I'm going to start this video with the answer to the problem I set you at the end of the last one, which was to determine whether or not two functions from r squared to r cubed were or were not linear. The first one was defined by t of a vector xy was equal to 2x plus y, 0, y minus x. That one is linear. And the other one was the same as the first, except in the middle coordinate you had a 1 instead of a 0. This one will not be linear. In fact, it doesn't obey either of the two linearity properties. All right. So linear maps between vector spaces were special types of functions between those vector spaces, and they were supposed to take into account the vector space structure in a specific way. In this video, we're going to see that in action. So for example, what we will see is that the image of a linear map will not just be a subset of its codomain, but a subspace. We're going to define two subspaces, or two things which will turn out to be subspaces associated with any linear map. So let's suppose we have a linear map T from a vector space V to the vector space W. Then we define the kernel of T to be the set of all elements of V which T maps to the 0 vector in W. And secondly, we define the image of T just to be the usual definition of image of a function. So the image of T is simply the set of all things of the form T of V, where V is an element of the domain capital V of T. We're going to show that both the kernel and the image are subspaces. In fact, the kernel will be a subspace of the domain V, and the image will be a subspace of the codomain W. But in order to do that, I need to prove a lemma, which is written just here. So the lemma says that if you have a linear map from a vector space V to a vector space W, then T of the 0 vector in V is equal to the 0 vector in W. So I've reminded you at the bottom of the screen here of what a linear map is. A linear map is defined to be a function with two properties. The first property is called respecting scalar multiplication, and the second property is called respecting addition. We're going to use those two, well, actually we're only going to use the second property when we prove that this lemma is true. So let's now do that. So for our proof, let's think about T of the 0 vector in V. Well, one property of the 0 vector is that the 0 vector is equal to the 0 vector plus the 0 vector. The definition of the 0 vector, or the defining property, is that when you add it to something, you don't change it. So T of 0v is the same as T of 0v plus 0v, just because 0v, the 0 vector in V, is equal to the 0 vector in V plus the 0 vector in V. That's a special case of the defining property of the 0 vector. Okay, T is a linear map, so by property 2, this is equal to T of 0v plus T of 0v. All right, we're now going to subtract T of 0v from both sides. Now I don't really need to put brackets in on this right hand side because I know vector addition is always associative, so it doesn't matter how I bracket this right hand side. Now let's look at what we've got on the left of this equation. On the left you have T of 0v minus T of 0v, so that is the 0 vector in the vector space we're working in. We're working in W. T was a linear map from V to W, so all these things are elements of W. And what we have on the left-hand side then is equal to the 0 vector in W. And on the right-hand side, T of 0v minus T of 0v is W, is the 0 vector in W again. So I've got T of 0v plus 0w. And again, the defining property of the zero vector in W is that when you add it to something, here t of 0v, you don't change it. So we just end up with t of 0v. Alright, so on the left I've got the zero vector in W, on the right I've got t of the zero vector in V, and that means I've proved the result which I wanted to prove. We're now ready to prove our result, saying that both the kernel and the image of a linear map are subspaces, and specifically the kernel is a subspace of the domain of T, which is called V here, and the image is a subspace of its codomain, which was called W. And I have reminded you at the bottom of this screen of the definition of a linear map, of the kernel and image of a linear map. So let's now prove this result. Let's prove part 1. First of all, so part 1 says the kernel is a subspace of V. So let's think first of all, what is the definition of a subspace? So you remember less than or equal to here means kernel of T is a subspace of V. What's the definition of a subspace? Well, the definition of a subspace has 3 parts. A subspace must contain the zero vector, it must be closed under scalar multiplication, and it must be closed under addition. So we have to do each of those 3 things separately. So first of all, T of the zero vector in V is equal to the zero vector in W by the lemma we just proved. That says precisely, look at the definition of the kernel at the bottom, it says precisely that the zero vector in V is in the kernel of T. That's part 1 of being a subspace. A subspace must contain the zero vector. Part 2 is that a subspace must be closed under scalar multiplication. So let's let V be an element of the kernel of T, and let's say our vector spaces are vector spaces over the field F. So then L will be a scalar, an element of F. I have to show that L times V is still in the kernel of T, because I'm trying to show that the kernel is closed under scalar multiplication. So what I've got to do is look at T of L times V and show that still the zero vector in W. Well, T of L times V is L times T of V because T is a linear map. V was an element of the kernel, so T of V is equal to the zero vector in W, so this is L times 0 in W, the zero vector in W. And we've seen that any scalar multiple of the zero vector is again the zero vector. We proved this when we first met vector spaces. So I've got here that T of L times V is 0, the zero vector in W, which means that L times V is in the kernel of T. We've now proved that the kernel of T is closed under scalar multiplication. The only thing left to prove that the kernel is a subspace is to prove that it is closed under addition. So finally, we take 2 things in the kernel. So let's let U and V be in the kernel of T. And I have to show that U plus V is in the kernel of T. So T of U plus V. Well, this is equal to T of U plus T of V, because T is a linear map, so it has to respect addition. But U and V were elements of the kernel of T, so both T of U and T of V are equal to the zero vector in W. And of course, when you add the zero vector to the zero vector, you get the zero vector again. So u plus v is in the kernel of t. We have shown that the kernel of t contains the 0 vector. We've shown that the kernel of t is closed under scalar multiplication, and we've shown that it's closed under addition, therefore it's a subspace, and we've completed our proof of part 1 of the lemma. So now let's do part 2. In part 2 I have to show that the image of t is a subspace of W, so I have to check the same 3 things for the image of t. I must show that the image of t contains the 0 vector, that it is closed under scalar multiplication, and that it is closed under addition. So let's do those 3 things. So we start off by showing the image of t contains the 0 vector in W, and we do it in exactly the same way that we did the kernel. So t of the 0 vector in V, by the lemma we did on the last slide, is equal to the 0 vector in W. And that's saying the 0 vector in W is t of something in V. In other words, that the 0 vector in W is in the image of t. That's the first part of the definition of being a subspace. The image contains the 0 vector of W. Now we're going to show that it's closed under scalar multiplication. So let's choose a scalar, L, and any element of the image of t. And an element of the image of t looks like the linear map t applied to a vector, little v in big V. I have to show that L times t of v is still in the image of t, because I'm trying to prove that the image of t is closed under scalar multiplication. But using linearity, I can write L times the image of t, L times t of v in other words, as just t of LV. But t of L times v, well, that's an element of the image of t. It's t applied to something, so for sure it's an element of the image of t. So L times t of v is equal to t applied to something, so it is in the image of t. We've shown that the image is closed under scalar multiplication. Let's now do addition. So I have to pick 2 elements of the image of t and show that their sum is in the image of t. Elements of the image of t look like t applied to u or t applied to v. So we'll take any 2 elements in the image of t, which we know are equal to t of something, t of u and t of v for some u and v, in the vector space capital V. I've got to show that t of u plus t of v is again in the image of t. This is easy because t is a linear map, so t of u plus t of v is equal to t of u plus t of v. And this is in the image of t simply because it's t applied to something in v. We've shown that the image of t is closed under addition, we've shown that it is closed under scalar multiplication, and we've shown that it contains the 0 vector, and therefore it is a subspace of W, and we've proved our lemma, kernels and images are subspaces. Let's compute some example kernels and images. So we're going to begin with a linear map defined by left multiplication by a matrix. So let A be the matrix 0, 1, 0, 0, and T subscript A be the linear map from R squared to R squared defined by TA of a vector x is just A times x. We showed in our previous lecture that this thing is actually a linear map. It really is a linear map because the linearity conditions are just familiar properties of matrix multiplication. So our question is, what is what are the kernel of TA and the image of TA. We'll do the kernel first. So a vector x is in the kernel of TA. Actually, let me write my vector a little bit more explicitly. So a vector in R squared looks like this. It's got two components, u and v. So this is in the kernel of TA if and only if TA of uv is equal to the 0 vector in the codomain, which is just the height 2 column vector 0, 0. And that's true if and only if A times uv is equal to 0, 0. Well, A is the matrix 0, 1, 0, 0. So if you multiply 0, 1, 0, 0 into uv, what you get is, in the first position you will get v, and then in the second position you will get 0. Okay, so that is true if and only if v equals 0. So here v is the second element of our vector. So the kernel of TA is all the vectors in R squared whose second coordinate is 0. You can see that the kernel really is a subspace, as we claimed on the last slide, because we actually proved this when we first defined subspaces. I think we used this or something very similar to it as an example of a subspace. Now let's look at the image of TA. So the image of a linear map is simply the image of the linear map considered as an ordinary function, has the same definition of the image of a function which we used when we first defined functions. So the image of TA is the set of all things TA of uv for all vectors uv in R squared. That's the definition of the image. So if we want a simpler description of this, we can look at what TA does to a vector uv. So TA applied to a vector uv, that's A times uv, so let's write A out. It's 0, 1, 0, 0 multiplied into uv. And then we did this before. What you get is v0, like this. So the image of TA is simply the set of all things of the form v0 for v some real number. So in this case, the kernel happened to be image equal to the image. That's just a coincidence. In general, the kernel and the image will be different. Because in general, for linear maps from V to W, the kernel and image are not even subspaces of the same thing. It just so happened that here we had TA going, the codomain and the domain of TA being the same, and furthermore, it turned out that the kernel and the image happened to be equal. So this is not true in general, even for linear maps which have their domain and codomain equal. So let's see an example of the kernel and the image being different things. So here is, we're going to look at now an example which comes from differentiation. So I'm going to remind you of a definition, r less than or equal to n of x. That means all polynomials in one variable x whose coefficients are real numbers and whose degree is at most n. So that is all polynomials that look like a0 plus a1 times x up to an x to the n, where x is some indeterminate, and a0 up to an are elements of the real numbers. This is a vector space when it's given the usual operation of addition and scalar multiplication that polynomials normally have. We'll then take d to be the function from this vector space to itself, defined by the differentiation map. So d of a polynomial f is the derivative df by dx. Then, as we saw in our last video, d is a linear map. So the fact that d is linear just comes from ordinary properties that you know to be true of differentiation. So ordinary differentiation rules tell you that the differentiation map is a linear map. We're going to investigate the kernel and image of this differentiation map. So the kernel of d, by definition, this is all f which are a polynomial of degree less than or equal to n in the single variable x, such that df by dx is the zero polynomial. Okay, well, which polynomials have derivative 0? Well, the answer is just the constant polynomials. So this is the set of all constant polynomials, all polynomials of degree 0. So those are the ones which are in the kernel here. So let's now think about the image of d. What can we say about the image of the differentiation map? So one thing I can say is that if you differentiate a polynomial which has got degree at most n, then the result will be a polynomial of degree at most n minus 1, because when you differentiate a polynomial, its degree goes down by 1, or if it was a constant, its degree stays at 0. So that tells us something about the image. It tells us that the image is contained in the set of all polynomials of degree at most n minus 1. So let's give a name to that subset, or subspace in fact. Let S be the set of all polynomials of degree at most n minus 1 in the variable x. You can check that this really is a subspace of the domain and codomain of our linear map D. That's easy to see because if you multiply a polynomial of degree n minus 1 or less by a scalar, you don't change its degree. And if you add two polynomials of degree at most n minus 1, well, you can't increase the degree, so the degree is still at most n minus 1. And certainly the 0 polynomial is in there as well, because that has degree at most n minus 1. I guess I've got a hidden assumption here, which is that n is going to be some number greater than 0. So D is certainly, S is certainly a subspace here. And the image of D is a subspace of S because when you differentiate a polynomial of degree at most n, the result is a polynomial of degree at most n minus 1. I claim that actually the image of D is equal to S. I know that the image of D is contained in S, so what I have to do is to prove that any element of S is in the image of D. So to do our proof, let's write down an arbitrary element of S and prove that it is in the image of our differentiation map. So we'll call this element little s, and I'd like some notation for its coefficients. So I can write it as a0 plus a1x plus, and I go up to an minus 1 x to the n minus 1. And that's what an element of capital S looks like. It's a polynomial of degree at most n minus 1. Now I want to find something which D sends to S. So I need a polynomial whose derivative is S. And also I need that polynomial to be in the codomain of our linear map D. So I need it to be a polynomial of degree at most n. All right, but I mean, that's easy for us to do. We can just integrate S term by term, and then we'll get something whose derivative is the same polynomial we started off with. So integrating term by term, I get a0x plus a1x squared over 2, and so on, just integrating every single one term by term, an minus 1 x to the n over s, over n. That is a polynomial of degree at most n. I say at most n because maybe n minus 1 is an minus 1 is 0, so I don't know that it has degree n, just know it's got degree at most n. That's a polynomial of degree at most n. Let's give it a name. We'll call it t. And if you differentiate t, you get s. So s is in the image of D. We've shown that the image of D is a subspace of capital S. We've shown that S is a subset of the image of D, so we know that the image of D is equal to S. And now we've completely described the image of our linear map D, and we've seen that it is equal to the set of all polynomials of degree at most n minus 1 in our variable x. So this is an example of a linear map where the kernel and the image were completely different.